All right. Alrighty. Good afternoon and good morning, everyone. Thank you for joining, and thank you. This is our 10-week series marathon that we are going for the last 7 weeks or so. We're in the 8th week. 2 more sessions to go, and this is the topic that's alumni requested, especially on the high performance computing. My name is Ravi Virmachaneni. I'm an alumni of SRKR 1989. I passed out from the ECE. Since then, I migrated to US in 94. Since then, I'm here and working on a lot of private sector and public sector. So my recent
కొంచెం ప్రాబ్లం మళ్ళీ ఫిక్స్ చేస్తున్నానండి అది కేస్
Srini, you need to go mute. Srini, you need to go mute. Okay, let me see. You can mute. Okay. All right. Sorry about that. So, yeah. So, since then, I think I predominantly worked in the private sector. Recently, I started working in the public sector. Last 7 years, I'm working as a chief engineer in Raytheon Technologies, based out of Washington, D.C. Raytheon is 1 second. I'm going to.
Mute all, I guess.
యా ఓకే
Sorry about that. So, with that, currently, as I said, I'm a chief engineer, chief architect on a NOAA program. It's called Office of Water Prediction. This is where one of the HPCs we were using. So I'll go in more details. Let me move on. So the topics, just a brief introduction, HPC fundamentals, the ecosystem on what are all the different technologies available, what are all the different real world applications, and at the same time what kind of challenges and best practices needs to be followed, and what are the future trends in HPC. So why HPC matter now? So as you all aware that the explosion of data and the complexity associated. So some metrics, according to Gartner, every day the kind of content that's being generated in several petabytes. No wonder, because the kind of content is being generated from so many avenues, and that's been very easy to do. Your mobile phone is the one that is a big content generator. So all these needs to be get connected, and some of the things that we need to do is the faster decision making requirements. So we're in the path of speed and the efficiency, the decisions we need to know right now rather than deferring to the later, right? And the real world impacts, such as climate change, that is real, right? So that's something. You see the seasons being shifted, or maybe unusual rains, unusual drought situation, or untimely climatical events that's happening. And the pandemics, the thing that we recently went through in 2020. Of course, the AI is the big game changer for a lot of things. Again, the global HPC market projected to be $66 billion by 2028. So I think there's a lot of reasons for that to be. So before jumping on to the high performance computing, I just put something together. What are the other computing platforms available? The traditional, which is just basically physical servers and personal computers, and that's what you usually have. You have your laptop, you have every control on it, and you can do everything what you can do on your laptop. But it has a limited capacity, capability that it can perform, right? Then the GPU based. This is where most of the GPUs started have as a purely gaming industry, and then they realized the potential of the GPU, how the multiprocessing can be take advantage, or parallel processing can take advantage of general purpose computing. Then that's where the AI and other things came into the picture. Let's look at the HPC. HPC is primarily it is aggregating computing resources. It's a clusters, or in other words, sometimes it is also called as supercomputer, right? So what's the difference here? When you use the traditional computer or a laptop or the system or the servers, the bigger servers, it has some limitations. So you definitely hit some limitations. So that limitations can be gone unless you basically bring the computers. We're not talking about the mainframes. Mainframes are gigantic machines that it is actually worked as a single unit. Whereas HPC, high performance computing, or the supercomputers, are basically a commodity hardware, but they can be worked in tandem. So they're all basically trying to do work in tandem. So the things that you can't accomplish in a single server, single workstation, or a computer can be done using the HPC. So it is how it is does this kind of things is primarily the distributed computing. So multiple connected internodes in a cluster, and high-speed networking, parallel processing across machines, and job scaling. I'll go each of these topics in more detail. So some key strengths in the area. So solving very large and complex problems where single machine can be handled. So it is extreme speed for the large data set. Remember, I was talking about the large data sets. So when you're dealing with the large data sets, there's a lot of other things that come into the play, such as whether it's a CPU, the number of cores that's available, or the how much memory you can handle on a single node, and that kind of things. So both memory capacity, high speed networking, large data sets, those are some of the strengths that brings into the table. So one on the far right is the quantum computing. It's an emerging technology. I don't want to go into the quantum. Quantum completely operates in different scenarios. I'm just give you a very high level. The traditional compute versus the quantum compute is a complete paradigm shift, right? So most of our computers are basically binary, right? 0 or 1. Everything is translated back into 0, 1. But in the quantum side, it is all about the superposition, entanglement, and interference. So it is much more complex than the regular classical computers. The concept of the qubit is in a superposition. It's basically the value between 0 and 1, anything in between. So there's a wide variation between those two. So I don't want to, the topic is not about the quantum, so I'm not going to go into the more details on that. So some key limitations. Let's focus on the HPC side. So what are some limitations on the HPC? HPC definitely high upfront costs, especially for those who want to set up on the on-prem, right? But it also has the complexity in management. So it can be mitigated. But it is a cluster of machines. You have to make sure that those are all working. So there's some kind of failures and other things happen. So how distributed computing is going to be managed and maintained and all that kind of things. Another important limitation is basically because supercomputers are special purpose, and it's basically working on a very complex scenarios and all those kind of things. Most of the times they are disconnected from the internet access. So they don't have a direct because of the security threats and other things that come into the play. Current typical problem domains and applications, academic and scientific research, astronomy, drug discovery, protein modeling, so on and so forth, and complex simulations, including airflow, nuclear weapons, in some places like design, for example, Boeing and other companies, they use for the design of the planes and other jumbo jets and other things. Optimization, financial modeling can be done, and logistics can be done. Weather forecasting and fraud detection, genome sequencing. Weather forecasting is the one I can briefly touch. That's where one of the areas that I'm currently working on. Current state of maturity, it is a highly matured environment. So with the evolution on the cloud, so this is one of the takeaway from this presentation. So previously it used to be, it is limited to the universities, bigger universities, and with scientific research and academic research and so on and so forth. Nowadays, it's no longer be the case. Actually, anybody can do the HPC kind of simulation workloads and everything on the cloud. So, which I will cover that as well in the subsequent. So there's some fun facts I want to present to you, especially where the origin and how the evolution of these HPC systems coming into the play. So back in the days during the World War II, that's the first time that Great Britain built this first 500,000 flops. Flops is floating point operations per second. So I'll give you how that flops can be done. Then in 1964, so roughly after 20 plus years, then 3 megaflops. So that's the first supercomputer with the 3 megaflops. Then Cray 2 in 1985. Another one with the over 1 gigaflop. ASI Red in 1996 was the first massively parallel computing reaching over teraflops. Then in 2008, that's a supercomputer with 1 petaflop. Then at the moment, we have exascale. So 1 exaflop are also currently available. So how do we measure this computer performance is basically floating point operations per second, because now we have hundreds and thousands of nodes working in tandem. So the determination of the flops is basically based on how many number of nodes, how many cores in the nodes, and the cycles per second. So the cycles per second is nothing but a clock frequency. So typically you might heard on the 2.4 gigahertz speed, right? So that's a clock speed. And then the flops per second. So the fourth term here is basically flops per second. How many floating point operations are done in one clock? So the mega flop is basically 10 to the power of 6, giga 10 to the 9, and exaflops is 10 to almost 18. So that's how the flops are going to be calculated. So what are some key characteristics of a HPC environment? First and foremost, it is a parallel processing. I don't know how many of you familiar with the recent, I won't say recent, almost 10 years ago, 12, well, 2008, 9 time frame, probably 12 plus years, right? So the open source implementation of the big data. So the harbinger for a lot of other things. So the technology evolves built on previously evolved some of the things. Look at how Java revolutionized. Internet first, and then the Java, then the open source. Open source introduces so many things that can be available, and easily built the newer innovative software and other things. So as more and more things are happening, if you look at the computers per se, we hit the hard limits at scaling up the CPUs, right? For example, after Pentium, there's not much happened, right? The reason is because we hit the hard limit. So the only way to scale these applications or systems is basically scaling out to attach multiple nodes work in tandem. So that's what it is. But big data, such as Hadoop and other things, basically brought to took some of these concepts from the parallel processing, MPI, massive parallel interface, and they each individual node work in tandem, and basically the concept of the map is basically how data is going to be chunked into multiple places and spread all over. And when you submit a particular job, they basically it works independently, and then it reduces to one single output. So that's what the typical map reduces. So similar concept, but this is basically the original concept came from the MPI, which is the supercomputers and HPC, high performance computing. So that's a parallel processing. So since this machine is so big and it has to be usually the one I'm working on, we don't have a direct access to this WCOS system, but that's a work by multiple agencies. That includes NASA, NOAA, and Department of Energy, and so many other folks. So when you're working on large computers like this, jobs has to be scheduled in advance and basically get the time, right? That's where the job scheduling is one of the important aspect of high performance computing. And the other one, speed and performance. So, how fast we can do things. Some of the things are related to the scientific related. For example, if you're looking at the hydrology, right? So there is a water cycle. The cycle has typical, from the formation of the clouds and actually getting the rain and going through the entire channel of getting to the streams and all the way to the rivers and the other things, right? So that has the implications. So all those things. So, but that's all the scientific methods you have to use. It's a pure science calculations that is. So for those to work fast, I think it is important to understand. See, if you're doing a weather forecast or the prediction, you can't be telling that, okay, it takes a couple of hours and I will give you the forecast. You can't be doing the forecast after the things have happened, right? But you can do the post analysis in a different way. But for the forecast to work in the real time, it has to be performed really quick and fast. The flexibility and scalability is an important aspect. So how it can scale or scale down, both the up and down, right? Also, I initially mentioned about the data sets. The data is getting bigger and bigger. And when you're dealing with a large data, and you obviously have to have a large memory available. So in some instances, we have almost a terabyte level capacity on a single node, just on a single node, right? So when you have hundreds and thousands of nodes, you can definitely bring all that data. Sometimes you have to put that everything in memory to do the processing. And with the latest incarnation into the cloud accessibility and cost savings, I think that's a big one. As a matter of fact, our current implementation, even though there's a on-prem HPC, our current entire implementation is a cloud-based HPC. Our solution is completely on the cloud. And we are supposedly delivering on the multi-cloud solution. So we try to not to be cloud native instead of cloud agnostic. I'll take a brief pause. I know I'm going too fast, I guess. So I'm going to take we'll slow down here. Anyone has any questions, comments?
I think I think you are at the right pace, and I don't think so. You're
Okay.
too fast, so we are following easily. Yeah.
Okay. Okay.
Unless others have any comments.
Yeah, one question though, actually, how do we assume it falls part of not GPU and into the HPC? And like, I mean, as of now, I mean, with my experience, it's just still GPU we reached where we develop LLMs. But you're talking a bit as one step ahead. And so what is the parameters, if you have that insights into like HPCs? Yeah, whether I understand as a use case, but what is the size of the data set, or what are the different features that you're looking into so that it falls into the HPC and not GPU? Do you have any
So Yeah, sure. Thanks for that question. So definitely. So GPU, see a lot of HPC systems, you can take advantage of a GPU as well. So there is no hard fast rule or limit that you can be using a GPU based HPC system. So the what HPC system bringing to the table is the availability of the resources at your disposal. Is that actually helps just for you alone? Definitely not. Especially I'm talking about on-prem systems. On-prem systems has the limits. For example, in our case, why we were not given any option to do some of these simulations that we are working on, not on the on-prem HPC, because they're exhausted. They don't have the capacity and things because NASA and NOAA heavily uses these systems. So some of the things what what we're doing is basically on the cloud and do the all the prep work, do the simulations, make sure that it's actually working, and you do all the different permutations and combinations to do on the cloud, and then actually go into the on-prem. So coming to the GPU concept, it is not limited. So HPC is just only CPU bound. That's not true. Okay, but you can actually take advantage of the GPU, but hardly, right now we're predominantly on the cloud, the AWS. Most of these resources are very expensive. Now, that's expensive is one part. Number two, with the AI and everything going on at the moment, some of these resources are very competitive, meaning availability of those resources, unless you actually go prepay that, okay, I need these dedicated resources. It is very hard to get the and compete against. Is that making sense? Or
Infrastructure perspective, you're saying like it would be more available than it helps you plan better, right?
Sorry, Krishna, we
oh,
can't hear you.
yeah, can you speak up a little bit?
Sorry, what I understood, am I audible now?
Yes.
Yes.
Yeah.
So what I understood from your statement is like it's when you move to the cloud and you plan the things of the resources, then it may be near equal to the GPUs, but for a different purposes in case of HPCs. Am I right?
No, I wouldn't say that. Okay,
I
I would say so.
back, yeah. You go ahead with your presentation. Probably I can connect. I just don't want to
Yeah,
deviate.
I'll come. So
Yeah.
definitely that's the area I will connect. So GPU can be used as well. Okay, I'm saying that there are HPC specific instance available on AWS, HPC 7 and all, but these are expensive. So you can get almost 968 GB memory per node, 196 cores. So that's a beefy node. There are instances where we are actually have to use that kind of nodes for doing the processing. But the GPU, we haven't explored the GPU option, but I do know colleague of mine basically working on a different program, same NOAA program, they experimented some things on the GPU based. Okay, but not in our program. We haven't done that. So let's look at into the resources what HPC provides. I think I already covered some of these concepts, the nodes and the cores, right? So uh, uh, systems like some of these exaflops and other things that I mentioned, have hundreds and literally have thousands of nodes, and each node may have several 196 cores or even higher and all those kind of things. So many compute nodes, many cores available, right? High bandwidth memory up to several terabytes. Even a single node can have a terabyte. So it's not that hey, entire HPC has a terabyte. No, it's a single node per node we're talking about. High-speed storage up to several petabytes storage for parallel IO. So that is a very important one. Probably you might be familiar with the Lustre file system on on AWS. Lustre is one of the fastest, but it is an expensive. So I think when it comes to, especially on the cloud side, so you need to be cognizant of the cost associated with it. Is it really need? So there are instances, for example, on the cloud side, if you are want a fast IO operations, especially intermediary data. So it's not the final state. So you can have the EFS and S3, for example, for the final storage. But if you want a faster transactions that's going in flight data, so this is where you should be looking at the high speed storage systems, such as Lustre file system. Network is very important. How much network bandwidth is available to you? In some cases, up to 50 gigabits bandwidths are there. Even InfiniBand and other things are available. So the most important is basically having a stable and efficient operating system, such as Cray is one of the operating system that's available. But there are a lot of other OS available on the HPC. Predominantly, it's Linux based. That's what it is. And so many softwares and applications, which I will get into more details when I go to the other side. So at a big picture, so how the architecture, this is just a purely very 50,000 foot overview. So on the left hand side, you have a client, your laptop or something that's been connected to with the concept called a head node. Sometimes some people call it a controller node. So it is just a different name. But what it is basically you're telling what needs to be done. Okay, this is where my data, this is what it is, and this is the job of MPI, massive parallel interface. What it tells is basically where is your data and how much of a course and other things that you be looking for. So you schedule with a software called Slurm is one of the most popular scheduler on the HPC, and that basically summits, right, that job. So the Slurm role is basically getting the available nodes, okay? And all these nodes are connected to a high-speed storage as well attached to it. Okay, it's not a per node. It's basically like a NAS and a SAN and that kind of parallel storage. So that's in the nutshell. So in big picture, as a user of HPC system, you log into the head node and you basically submit your Slurm job. So that job will be get kicked off on available nodes. And once the job is done, it brings back all the results to you. So that's at the notch level. So this is the little bit lower on the job scheduling. Your login node, you have a script, you submit the job, and it will be queued up, and it can be scheduled immediately, or it can be scheduled on its own so date, and that's pretty common for a weather forecast. So you have a short range weather, long range weather, and medium range weather. Usually, short range weather is basically every couple of hours. Medium range is a couple of days. A long range is basically going all the way, the forecast goes all the way to a couple of months, or at least 30 days or over, or sometimes even annual forecasting as well. So that's how the very high level how things work. And it is the scheduler's responsibility to get the compute nodes, what are available, how start the job, and collect the information and send the information back to the user. So the one I'm showing here, HPC in the cloud. So how things work in the cloud. If you have a native cloud implementation, okay. So one of the key concept in AWS is AWS parallel cluster. That is the one basically negotiating everything for you. So here there are four main zones. One is the access zone on the top left. you have that's where the login node happens, right? So you are actually giving the access to the nodes and other things. Then there is a management zone. This is where the controller, or if you have a access control and other things that it can be connected to, making sure that you have that. And then there is a Slurm DB, which is a database. In this case, it's a MySQL. That's where it captures all the runtime information and everything. Slurm is the scheduler. So the other zone here is the third zone on the top left, top right is basically compute zone. This is where the compute EC2 instances are available. You can have multiple compute zones. You can segregate subnet with there's no limit. So it's a elastic compute, right? So you can basically extend this. The last one on the bottom here is basically data storage. That's another subnet, basically having you're attaching the shared storage such as EFS I mentioned earlier, and FSXL, which is the cluster file system. That's also, and we also use the S3, for example, if you want to put some results back and share with others. Everything else is basically these are for monitoring. CloudTrail and CloudWatch and Secrets Manager, those are all the monitoring. And this is currently showing as just a one region. You can extend this into a multi-region. You can extend this into multiple availability zones. So this is a very high level, simplistic view of how you can implement HPC in the cloud. So the key concepts here goes back to the AWS parallel cluster. That's a concept that's been used for the HPC on AWS. The other one is these compute nodes are HPC 6 and HPC 7A. Those are the two specific. It doesn't mean that you can't be using other regular nodes like CNs and other things. So that's also a possibility. So you can definitely use it. Storage, like I said, that is a shared storage, right? So EFS is commonly being used. Okay. Any questions here? All right. I'll move on. So what's a software stacks looks like? So I mentioned about the operating system. So predominantly Linux based, whether it's a Red Hat, CentOS, or Ubuntu, or even SUSE Linux and other things. Those are all available. Login is usually SSH or GSSISH. File transfer, SCP, and a couple of commercial tools like Grid FTP, Globus from Globus. Middleware, that's where the main how the parallelization actually works. Okay, so okay, I'm submitting a job. So how all these are going to be, this is the crux of it. So OpenMPI, that's the open source version of it. And Intel is currently we use the Intel version because it has the highly optimized compiler. So I think that actually gives a better performance. Previously, it was a licensed software, but Intel opened up and it's no longer, you don't need the license. But I strongly recommend if you want to use any MPI applications, take advantage of the Intel MPI. All the software management is the concept of a module. So you can load the modules and you can bring your own every software that you're basically working on. Compilers, Intel, GNU, and PGI. So Intel compiler, like I said, that's the one we're basically using. So you do have a debugging and profiling tools. Unfortunately, I did not use any of these tools, and these are all maybe on the traditional HPC systems. I did not get a chance to do any profiling at the moment. Job scheduling, Slurm. I was talking all the time Slurm, so I've been more familiar with the Slurm scheduler. The others are also equally good. So when coming to the containers, the only thing that is available at the moment, especially for on-prem, is the Singularity, especially the one we are dealing with. They don't support the Docker. Docker has the issue, assumes that root privileges, right? So that was the reason Docker was not taken into account or not supporting, whereas Singularity does not need the root privileges on the node. So that's the one. So coming to the languages, C, C++, Fortran, Python, Perl, and you see there's no Java here, right? So you might surprise Fortran. So back in the days when my first computer course is actually in Fortran, I remember the very first computer in SRKR, and it's only one lab technician, so we have to use the punch card. So I don't know how many of you familiar with the punch card. So punch card, and you give the punch card to the lab technician, and 2 days later he will tell you whether your program worked or not, right? So that's my first experience starting into the computer realm. Interestingly, that Fortran, after 30 plus years, it came back to me. Luckily, some of these things I'm not working, so I'm not the guy basically doing the deep under the weeds, but being an architect, I don't have the time to do this kind of low level, but my team, about roughly 50 members in the team, some of the legacy modules, they're still in Fortran. You will be surprised. There is an opportunity for me the other day came, and I actually looked into Fortran. Interestingly, Fortran also has the object-oriented Fortran. Okay, there's a lot of new concepts came in, but we're not taking advantage. At one time, I was proposed to the government, basically we should take a look at take advantage of some of these legacy code and take advantage of the object orientedness and other capabilities, multi-threading and all those things came into the picture. But they're still stuck at Fortran 77, and parts of some of the code is Fortran 90. Now there's a Fortran 2008 and there's a Fortran 2022 or something like that. So there's a lot of things have actually evolved. So, but the important point is basically the technology stack is limited. So I think a lot of things can be related to the efficiencies and the speed and other things. That's most important. So that's why you have a very limited number of languages available on the HPC software. Real world applications. So when it comes to climate modeling, and that's the one we're not doing on the climate side of the equation, but we are doing the water prediction, flood forecasting, and others. Genomics and drug discovery, financial risk modeling, AI modeling also be done. So a lot of ChatGPT kind of GPT models, a lot of simulation work, engineering simulation work as well. So one thing I want to get into the area that I familiar with, this is the one I was referring to earlier when I said WCOS. It is weather and climate operational supercomputing systems. This is a recent incarnation. So the current compute power for this is 12 petaflops. Okay, but it has a redundancy. There are two identical supercomputers. One is a Dogwood in Virginia here, and another one Cactus in Arizona. So they are located on two different power grids because, I don't know how many of you familiar, few years back when there's an entire blackout happened in Eastern Seaboard, lot of, even though you have a high availability, but if you're situated in the same geolocation, you are vulnerable to the power grid failures. So for that reason, you have to make sure that you are actually geographically diversified and ensure that your high availability is going to be the case. So that actually helped me in one of the implementation for FAA. So I was working on a Federal Aviation Administration proposal program. It's a $5 billion proposal. It is basically, I don't know, most of you might heard about 5.9 availability. 99.999. So that gives you very minute time for any kind of upgrades or anything. So I think if you do a simple Google search, it will tell you roughly 24 minutes or so per month. So there's not much time for the downtime, right? So in that case, that you have to build the resiliency into the system and understand all the fault tolerances that needs to be in every step of the way. No single point of failure. So how do you build a plan A, B, C, even D? See, if it happens, two things goes down or three things do I still have the ability, especially life critical systems, such as in case of FAA. FAA predominantly every communication that goes on the from ground controls towers all the way to the pilots, right? They're constantly in communication. So weather is the big factor that influence that. And if something goes wrong, you have to be diverting the teams communication. So very in an efficiently and a timely manner. I know a recent incident that I think last year, right? Last year or early this year, uh, at Reagan Airport. There was a miscommunication, that the communication did not go through, and there was a crash. And what happened? The loss of life, right? So this is that's where it is very, very, very important to build a network. Otherwise, if you don't feel safe, or you think you can take the flight, probably not. So that's an important one. So
Yeah, Ravi, just a time check. We have about 8 minutes more left. Yeah.
yeah, 8 minutes left. Okay, sure. Yeah, I'm pretty much winding down here. So
Okay.
some of these models here. So the production, they call it as NCEP, National Center for Environmental Prediction, Production Rate. So it runs millions of models on a daily basis. Okay. So some models are very high resolution with realistic physics and weather and climate. So multiple data source comes, data coming from the weather satellites, whether coming from the ground observations, and a lot of feeds that comes in. So you should be in a position to forecast these in a real-time fashion. So hurricane forecasting is one of those applications, and global forecasting, rapid refresh forecasting. So those are all the weather related. The one I'm working on and the one at the bottom, National Water Model, it is a continental scale, especially continental USA. Operational hydrologic model system developed by NOAA to simulate forecast and water movement across the United States. So in a nutshell, this one is we're still working on it. They have the existing application that's written several years back, one big gigantic model. So the difference here is basically not the motivation for this national water model is basically identifying the places where the flood is going to happen or the drought situation is going to be, and timely saving the property as well as the casualties, right? So minimize the casualties. So loss of life and other things. I think we can attribute to one recent incident, probably you guys might have heard about. Happened in near Dallas. Remember the overnight rain that caused the flash flood, and I think it was an unfortunate. I think even though the alert went out, people basically in the sleep, they did not get, maybe because of the because of the remoteness. So I think there are some following actions taken how we can actually prevent these kind of things happens in the future. So I think for that reason, it is very active, even though government is shut down. Our program is still active because of the seriousness of the need. So some challenges in HPC, of course, cost of infrastructure. So if you want to do it on-prem, that's very expensive, and that's where the HPC and the cloud comes in handy. Energy consumption sustainability is an important thing that needs to be addressed as well. Software parallelization complexity. So it is a different thought process that you need to understand how the MPI and parallelization actually works, unlike the traditional computing. Data movement bottlenecks. So moving the data from place to place, and that's another challenge. It typically be the case because you need to bring the data in, and sometimes maybe the whatever you're taking out is maybe not that much, but there's a lot of noise in that data. So some of those are important to consider. Best practices, efficient scheduling and load balancing. So you understand your workloads and make sure that you schedule your resources. This is especially true in a shared environment. But if you're doing it on the cloud, then also there is different things that you need to be considering. Whether you pre-purchase some of these. Right now, we're kind of we didn't have a established pattern yet how system can be used at leverage. So for that reason, we're taking a little bit of on demand at the moment, but sometimes it is just getting frustrated. Users are getting frustrated because the resources are not available. So it is important to understand your workloads. It is important to understand how you can get those resources available on that. Hybrid models, that's a pretty possible. That's what we are doing currently. Everything on the research side, on the development side, happening on the cloud. Once we are into a decent shape, and we're basically moving into the on-prem. So all the models are supposedly running at the end of the day, running on the on-prem HPC. Performance checks, and this is something actively we're doing it at the moment. We're doing a lot of benchmarking, understanding the various loads, workloads, and do the benchmarking. That is an important best practice. So looking into the future trends, so there is a exascale computing. It's a 1 quintillion operations per second. So I have the resources in the next slide you can take into AI and HPC synergy. There's a lot of things that can be taken advantage from the AI. Quantum and HPC hybrid systems, so that's also, these are the future trends. So we're not there yet. That's something that can be done. And democratization via cloud HPC, and that's happening. That's right now, the first and last are happening at the moment. The others are in the exploratory stage at the moment. So I shared some resources here. Take a look at the Lawrence Livermore National Lab, where it has the HPC tutorial. There are a couple of other agencies in Europe also has some of the HPC tutorials that you can take a look at it. I mentioned about Department of Energy, supercomputing, exascale side. There's a pretty good information there. So that's also an important one. El Capitan is the Lawrence Livermore National Laboratory. That's the one with the fastest supercomputer exist to date. So that's El Capitan. So all these links are actually reachable. So I'll be sharing. That's pretty much it. I know, sorry, I have to go too fast, but I hope it is useful.
That's good. Let's see if anyone has any questions.
Yeah, Ravi, it's a great topic. It's much needed topic in this current world. You know, everybody is going with big data and AI nowadays. So it's very valuable. And one quick question, Ravi, this is something we can always discuss later also, but if we don't have much time. But again, any software, right, the latest softwares in cloud, for example, I'm taking my field as for HANA. They're coming with some AI features enabled. How do you make sure the current setup is done in a right way so that it can take the loads of AI and the performance, like benchmarking we're telling, there are some steps we can follow. There are some tools available. How can we check that to make sure we are expected performances we are getting?
So it is always a platform specific tools. So I shared a couple of them
Right,
in the
right.
presentation, right? So
Mhm.
it's a depend on what your environment is. So if you
I
have
think
a
that makes sense.
Python based,
Mhm.
if you have a Python based, probably you will use
Right,
Python specific profiling and other things.
right.
But there are HPC specific. But
Tools, yeah.
with the democratization with the HPC and on the cloud, I think there's a lot more tools available. Maybe take advantage of the one that is natively available rather than things that you can actually.
No, that makes sense. Yeah. So that's so I think for specific to that environment, they may have their own tools. As can be AWS, Azure, wherever you are running, right? That's what you're
Right,
saying.
right.
Correct. Got it.
Yeah.
Yeah. That's the only question. Otherwise, very useful, more technical, unless you go through all those. And if you're specific to that field, a lot of these things you may not be able to understand too. That's fine, but it's a good topic.
Yeah, but the important is basically the how HPC is getting in
Yes.
the hands of anyone with the cloud. So
Right.
cloud made it available. So
Correct.
you don't have to shy away from, oh, I have a too big of a data, so I don't know how to do this. I think there's a lot of resources available. And of
Right.
course, the most important aspect on the cloud is the cost.
Right.
See, is it right? Or what kind of instance you will be running? That kind of
Right.
thing.
Yeah, there are some benefits with the cloud also. With my experience, of course, others can chime in. The advantage is some of the systems, when you don't know, you can turn it off on the cloud. That way, you don't have to pay. It's
Yeah.
a non-production system. I don't use on weekend. That's how we manage our cloud costs. Again, they're all. You're right. They're expensive. You take a contract 3 years, they may reduce 30% price. All that you have to work it out.
Yeah.
So, but the cloud is more flexible. Yeah.
Exactly. Say on demand, and you can use with
Exactly, based on your needs. Yeah.
Yeah.
Yeah, good presentation, Ravi. Thank you.
Yeah.
Thank
Good.
you
Very
for
good.
that.
Yeah. Very good.
Yeah. Any other comments before we sign off? Okay. Thank you very much for your attendance, and really enjoyed the conversation here. Thank you.
Thank you.
Thank you, everyone. See you all again next meeting. Yeah, thanks.
Sure.
Thank you.
Thanks.
Thank you.
Bye.
Yeah.
Thank you all. Bye.